right, here we go. Lesson number 2 for the week. We're going to look at 3 gas laws today. Again, it's just learning how to use the formulas. We're not going too deep beyond that for this, so don't get too stressed out, okay? The first one, we're going to jump right in. Not a ton of theory behind it. We call it the combined gas law. Why? Because it combines 3 other gas laws into one. So it'll relate Boyle's law, Charles' law, we learned about those, and also Gay-Lussac's laws. I didn't run this one with you guys because we basically only teach it so we can go right into the combined gas law. So what do we know about these? Well, I know that Boyle's law is P1V1 equals P2V2. Charles' law is V1 over T1 equals V2 over T2. I also know, and you don't know this one yet, but here you go, that Gay-Lussac's law is pi over ti equals puff over tuff. Now together, all of these have a constant temperature and a constant amount of gas, so a constant number of moles. That means we can put it into the combined gas law. Okay, the combined gas law is P1 V1 over T1. You got it. Is P2 V2 over T2. Pi vi over ti equals puff vup over tuff. Sorry, I realized up here, constant T is not always the case since temperature is changing in 2 of them. I looked at the wrong spot on my master copy. What's constant? The number of moles. Let's jump right in to our example. We've got a small balloon. It's pretty small. It's containing 275 milliliters of helium gas at 25 degrees Celsius and 350.0 kilopascals. I want to know what the new volume be when the temperature drops to 10 degrees Celsius and the pressure drops significantly to 101 kilopascals. Write out what we know. V1 equals 275 milliliters. We can keep it in milliliters as long as we know our answer will be in milliliters, because this is proportions and ratios. We know that P1 equals 350.0 kilopascals and T1 is 25.0 degrees Celsius. Remember to put that into degrees Kelvin, so 298 K. P2 is 101 kPa and T2 is 10 degrees Celsius or 283 Kelvin. So pi vi over ti equals P2V2 over T2. We want to get V2 by itself. So both sides are going to be multiplied by T2. Both sides are going to be divided by P2. So we're left with P1 V1 T2 over T1 P2 equals V2. Whoa. Fill in these values. So 350.0 kilopascals times 275 milliliters times 298K, nope, 283K, T2. Divided by 298K times 101 kPa. And that's going to give us our final volume, which we will see is 905 milliliters. So you might be thinking, okay, but the temperature dropped, and so the volume should drop. You're right. However, the pressure dropped, which means the volume would increase. And that was a significant pressure drop. So we're going to see the volume increase from pressure override the volume decrease from temperature drop. Therefore, the final volume of the balloon is 905 milliliters. Done. That's actually the only example I'm going to be doing for combined gas law. But all of it is just writing out your given, rearranging your equation, and solving. And you definitely have some textbook questions to practice with that one. Up next, we have gas law number 4. This is Dalton's law of partial pressures. You'll like this one, I promise. All right, so I'd like you to imagine you are making some punch and you put in 100 milliliters of orange juice and 100 milliliters of grapefruit juice and 100 milliliters of club soda. What would your final volume be? You'd add them together and it would give you 300 milliliters. That's the same thing, but with gases and pressures instead of volume. So Dalton's law of partial pressures states that the total pressure The total pressure of a mix of different gases is equal to the sum of the individual pressures. In formula form, Dalton's law of partial pressures, the total pressure is equal to P1 plus P2 plus P3 and on and on and on. Let's try a quick example. Hey, millimeters mercury. I told you we'd see it again. Okay. A canister of compressed air has a total pressure of 182 millimeters of mercury. The container contains oxygen, which accounts for 51 millimeters of mercury, carbon dioxide, accounting for 11 millimeters mercury, and nitrogen. I'm asking you what the pressure of nitrogen is in the container. Well, we know that our total pressure is 182 millimeters mercury. Our pressure of oxygen, so PO2, is 51 millimeters of mercury. Our pressure of carbon dioxide, so PCO2, is 11 millimeters of mercury. And we're looking for the pressure of N2. So the partial pressures of all of the gases in the container will add up to the total. So that means that the total pressure minus that of the oxygen minus that of the CO2 will equal the pressure of the nitrogen gas. And that's all it is. And that leaves us with 120 millimeters of mercury. Remember, sig, digs, and adding and subtraction is about decimal places, not number of digits. That means the pressure of nitrogen in the canister is 120 millimeters of mercury. Say so. That's it. That's gas law number 4. Easy peasy, right guys? Okay. We are going to go on to our last little bit of information here. We need to look at moles of gas now. So when we talk about molar gases, we need to talk about some standard conditions. We have 2 sets of standard conditions that we use in gas laws. We first have STP, which stands for standard temperature and pressure, right? STP makes sense. So this is a temperature of 0 degrees or 273 degrees Kelvin. The pressure is 101.3 kilopascals or 1 atmosphere. And the molar volume of a gas at this condition is 22.4 liters per mole. So this means for an ideal gas, and you need to have done that kinetic molecular theory to know what I mean when I talk about ideal gas. But an ideal gas at these conditions, so at this temperature and pressure, will take up the space 22.4 liters for every mole of gas that's present. Got that? Now what we also have is SATP. This is standard ambient temperature and pressure. So if you're a scientist, we're probably not encountering these temperatures and pressures all that often. Okay, this is at sea level, and that's 0 degrees Celsius. Burr. Ambient is more room temperature conditions. So this is where we see that we have a 25 degrees Celsius temperature, a little warmer than usual, unless you're, in O'Neill in June, which we're not. But that would also be 298 Kelvin. Our pressure has moved up from sea level to 100.0 kilopascals. And because the temperature has increased and the pressure has decreased, we're going to see that our molar volume, so the volume occupied by 1 mole of an ideal gas, has increased to 24.8 liters per mole. Be careful you don't fall into the moles per liter trap of concentration. So you need to remember these because you will see questions reference a gas at STP or a gas at SATP, and you need to have these handy or locked in your brain so that you know this. Ready for gas law number 5? We're back to Avogadro's law. Remember when we started with Avogadro back at the start of stoichiometry? It just sticks around for us. Why is this Avogadro's law? Because it relates to moles. So this law says that equal volumes of ideal gases at the same temperature and pressure contain the same number of moles. In formula form, what is Avogadro's law? The number of moles divided by volume equals number of moles divided by volume. What's constant here? Temperature and pressure. Put it into action. At STP, 1.0 moles of carbon dioxide has a volume of 22.4 liters. What mass of carbon dioxide is present in a 3.0 liter sample? Well, N1 is 1 mole. V1 is 22.4 liters, right? 1 mole, 22.4 liters. N2, we don't know, but V2 is 3.0 moles. So N1 over V1 equals N2 over V2. We're going to divide or multiply both sides by V2. So N1 V2 divided by V1 equals N2. So 1.0 moles times 3.0 liters divided by 22.4 liters equals N2. That gives us, we need 2 sig digs, 0.13 moles. That doesn't finish the question because we're asked for the mass. If only we knew a way to convert moles into mass. Hey, we do. Right? So mass is equal to the number of moles times the molar mass. That's 0.13 moles times molar mass of carbon dioxide is 44.01 grams per mole. That leaves us with 5.7 grams. The mass of carbon dioxide in a 3 liter sample at STP, that's important, is 5.7 grams. And that, folks, wraps up lesson number 2 of our week. So go ahead, try these problems, and come on back for our last piece, which is the ideal gas law.